Hello and welcome to another introductory statistics instructional video. Today we're going to walk through an example of how to fill out an ANOVA table. This is covered in the video lectures we use for the course, but there's a trickier part of this table that I want to go over. So to fill out this table, the two first columns for degrees of freedom and the sums of squares, those columns are pretty straightforward. The degrees of freedom for treatment and the degrees of freedom for error have to add up to your total degrees of freedom. The same thing goes for the sums of squares column. So depending on what space is missing in the table you would have to adjust your arithmetic accordingly. Since we're missing our degrees of freedom for treatment, but we have the degrees of freedom for error and total, we can find those degrees of freedom that are missing by just subtracting the degrees of freedom for error from the degrees of freedom for total. So that tells us we're missing an 8 right there. We have the sums of squares for treatment and the sums of squares for error, so we just add those up to get our total. So 144.452 is our total sums of square. The mean squares are a little bit less straightforward. What the mean square is a measure of that variability, but it's scaled back based on the degrees of freedom. To find the mean square for a given row, you would take that respective row's sums of squares and divide by its degrees of freedom. So to find the mean square for treatment, I would take the sums of squares associated with treatment and divide by the degrees of freedom associated with treatment, giving me a mean square of 4.829. Same thing with the error row. Take the sums of squares associated with the error and divide by its degrees of freedom, which gives us 1.556. So degrees of freedom and sums of squares you work in your columns, and then mean squares are calculated using the whole row. Your F-test statistic here is just going to be the ratio of the mean square treatment divided by the mean squared error. So once again, we go back to our calculator, 4.829 divided by 1.556 gives us an F statistic of 3.103. Now, the probability greater than F, you'll sometimes see it written that way, or you'll sometimes just see it written as the p-value. This is the same p-value that would be calculated if we ran through and did this ANOVA test in StatCrunch normally. Like with the t-tests and the proportion tests, this F statistic here is a value from a distribution. It's a new distribution we haven't worked with yet called the F distribution. And like the standard normal and the t distribution, we have a calculator that we can work with in StatCrunch. So we take our F stat, plug that into this calculator here, 3.103. Now an F distribution is defined by the degrees of freedom. Here you'll see num or numerator degrees of freedom. That's the degrees of freedom associated with your treatment. We had a treatment degree of freedom as 8, so our numerator degrees of freedom would be 8. And then den or denominator degrees of freedom is the degrees of freedom associated with your error. How I like to think about it is when you're looking at a fraction, the numerator is the number on top and the denominator is the number on bottom, and your treatment row is on top of your error row. When calculating these p-values, since the F distribution is right skewed, we always want a greater than. Remember that the p-value is the probability of being as extreme or more extreme than your test statistic. We can't really get more extreme if we go to the left in the F distribution because it's backed up at 0. So when calculating the p-value with the F calculator, always, always, always find the probability of being greater than your test statistic. And this gives us a p-value of 0.005. Alrighty, I hope that clarifies how we would fill out an ANOVA table. This p-value is a little bit trickier, but it's still worth knowing how to calculate that and how to work that F calculator. Alright, that's going to be it for this video.